Hello and welcome to this lecture on fatigue design. What we will cover today will be on how to compute cumulative fatigue damage in case we have general loading in the form of an alternating stress and a mean stress, and also if we have random loading. So these kinds of situations require entire knowledge of how to do the fatigue design. The main rule that we have here for accumulating damage was developed a long time ago by the engineers Miner, and then later in the 60s by Manson. So we'll just mention what is the Miner Rule and what is Manson's rule in computing accumulation of fatigue damage. So if you look here, you see that we have two main rules. The first one is the kind of the fundamental, which is the Palmgren-Miner, the name of the two engineers who developed it. And then later we will discover that this rule doesn't account for cumulative damage from one cycle, from one block of cycles to another. So there's a little bit of modification by Manson. So the idea is very simple, and idea is that if we have a completely reversed loading, fully reversed cyclic stress without any mean stress, and it's only one component of stress, we don't have multi-axial loading, then in this case we can compute the total number of cycles to failure. Suppose that this total number of cycles to failure is 1,000 cycles. Let's say 10,000 cycles if we are considering a high cycle fatigue situation. And suppose that we used the component at this particular level of alternating fully reversed stress for only 2,000 cycles out of the 10,000. Then the simple idea of Palmgren-Miner is that there is going to be a cumulative damage in the material of 2,000, which is the number used, divided by 10,000, which is the total number that would make the material fail. And therefore, the material has been consumed to the tune of 20%. So you have a damage that accumulated of 20%. Now, if you use it at different levels of amplitude, applied amplitude, you can do the same and find another fractional damage and so forth. And then if the total damage that's accumulated in the material reaches 100%, we can consider that the component has failed. So the simplicity is that we can define a damage fraction, and the damage fraction is the actual number of cycles that are used divided by the allowable number of cycles. And allowable is the number that will cause failure at this particular amplitude. So suppose that I have a fully reversed amplitude, sigma fully reversed, and I'm allowed capital N cycles, say 10,000 as an example, but I used only lowercase n 1, suppose that this is 2,000. So the example that we have will be 2,000 divided by 10,000, and therefore the amount of damage is 0.2. So you can imagine that we can repeat this situation for another level of amplitude and find a different kind of damage fraction, and therefore the sum of all the damage fractions should be equal to 1. So this kind of situation would be, if you look at the time domain, then you would have a certain number of cycles of amplitude 1, like this, and then this is followed by a different number of cycles with amplitude 2, and so on. So this is for sigma amplitude 1, and this is sigma amplitude 2, and therefore you find the damage D1 that corresponds to sigma amplitude 1, and the damage D2 that corresponds to sigma amplitude 2, and so forth, to get the total accumulated damage. So let's take an example here. An example that you see is that they summarize the PM rule in the sense that the sum of all DI should be equal to 1 divided by the factor of safety, in case we require that we need a factor of safety. Otherwise, if the factor of safety is unity, then this will be equal to 1. So in this example, we have two types of cycles. The first amplitude is used for a number of cycles of 3,000. And the total allowable at this amplitude is 8.52 times 10 to the 3, as you can see here. So D1 in this case is 0.352. And then we added to this another amplitude that is lower, and this amplitude was applied for 100,000 cycles, and we allowed 500,000 cycles in this case. So the damage accumulated is 0.2. So if these are the total number of cycles that are used, then D1 plus D2 is equal to 0.552, and therefore if you want to compute the factor of safety up to this point, it will be 1 over 0.552 would be 1.8. So this is kind of an example that you can illustrate it here, where this is the SN curve. Usually S is a log plot versus log N. You have here capital N1 is used up all the way to the end. This is that capital N1, but we use only lowercase n1, so that resulted in 0.352 of fractional damage. And then the second level of cycle is lower amplitude, and that resulted in capital N2 of 0.5 times 10 to the 6, and we used up only 10 to the 5 up to this point. So we use this part only, and not the total capital N1. So this is N2, and this is lowercase n2. So that's kind of the way that we would use fatigue calculations to accumulate the damage on the basis of the very simple PM rule. Well, you can see from here that there's some weaknesses of this rule, because if suppose that we apply a large number of cycles that makes the material weak, as the material is used up in fatigue, it doesn't become as pristine as it used to, and therefore the damage will make it weaker, and therefore we would expect that the SN relationship that we developed for the virgin material should not be the same as the SN relationship for a material that has been consumed already, in a sense. So that's the idea of correction for damage accumulated. In other words, if I go from the first block N1 and I calculate the damage is 0.35, therefore I have to go back and then make a small change in the SN relationship so that I can make the material weaker, essentially, and then after this step I can go ahead and recalculate another amount of damage that is computed. So this is one aspect that we have to deal with. Another aspect is that suppose that we don't have a fully reversed stress applied. What do we do? Well, in this case, we have to consider the effects of the mean stress that is associated with the component of applied stress, which means that we must use the ideas developed by Goodman or Gerber or the ASME or elliptic equations, and then we make a correction for the mean stress, meaning that the alternating stress effectively would be higher. Once you have a mean stress, then effectively, which is a reversed, equivalent reversed stress, is higher than the alternating. And then we can use, again, the same SN relationship. Now, the last item that I wanted to discuss is that suppose now that we have a complex stress state, a stress state that has axial loading, torsion, and bending, and the oscillating, and also making mean components and so forth. Complex stress state similar to what we will design for our shaft assembly and the power transmission system. Well, in this case, we have to go through a step, and this step would be to summarize all of the stress components into an equivalent von Mises single value, and this single value will be for the alternating part, another single value for the mean part, and then we make a correction for the effect of the mean using one of the fatigue relationships that we've learned before. And once we do that, then we can use the SN curve and successively add the damage. Well, the final point here is that on top of this, suppose that I have random loading, as you will see in your crankshaft design. In the crankshaft design, you will see that the loading on the crankshaft to produce complex stress state, and also it will produce cycles that seem to be random, like some up and some down, and they repeat like in blocks, but each block has a lot of valleys and peaks. So in this case, what do we do? How do we convert this stress profile into something that can be computed? So this is a kind of a summary, and let's just go back and make a discussion of how we do the steps in the calculations. So the first step in fatigue design is that if we have a matrix of sigma matrix, sigma ij, then we have to convert this to sigma von Mises, which is equivalent stress, and that will be for the mean and also for the alternating. So this is the first step, and that, this step comes from conversion of the load to equivalent values of the stress components. Then we check to see if the number of cycles is less than 1,000. If this is yes, then we use the strain life approach that we have described before. If it is greater than 1,000, then we can use the stress life approach that we have learned so far. Now next, suppose that we discovered that we have n greater than 1,000. Then we check on the alternating component of the stress. Is it fully reversed? If it is yes, then we use it as is to be the sigma reversible. If it is no, then we have to correct for the mean stress, and we have a number of possibilities for the correction of the mean stress. For example, the Goodman, we use the relationship, the sigma reversible is the same as sigma applied, but amplified by the damage fraction caused by the mean stress, because 1 minus sigma mean over sy will make a smaller fraction in the denominator, and that would amplify the alternating stress, and that's kind of some way to make a conversion to a reversible stress. And then next we find the constants A and B in the fatigue SN relationship, as you can see here, and that once we have SF, we have to relate it to sigma reversible, and this relationship comes through the fatigue factor of safety. So simply we can assume that SF is the fatigue factor of safety times sigma reversible. So if we require a factor of safety of 1.5, then, and we have a mean stress, then number one, the alternating stress has been amplified to become sigma reversible. Number two, sigma reversible has become amplified to become NF, which is 1.5 in our case, times sigma reversible. And once we have SF, then we use the constants A and B to determine the relationship between SF and N. And in this case, we are assuming that we have one single amplitude of SF1, say, to produce N1. And suppose that we used only a number of cycles lowercase n1, then we can determine the damage fraction, which is lowercase n1 divided by the allowable. And the allowable is obtained from the SN curve. And we can then repeat for other cycles in the duty cycle, such that we add up all of the damage to be equal to 100%. So we will use the Palmgren-Miner or the Manson to recalculate the SN for subsequent cycles with the damage. And hence the total damage should not exceed 100%. So this is kind of the procedure that we have for a general calculation of the fatigue. And what I will do now is I'm going to give a specific example of loading cycles on a component, and then we will go through the steps in these calculations. So let's do that. Here we'll take an example, and in this example we have let's say, see the example here is a stress cycle that, as you can see here, we have the stress cycle is let's see, trying to adjust the, yeah, here we go. So as you can see, for this example we have two types of cycles, and the two types of cycles are, one of them goes from 60 up to 80, down to 40, and then back up to 60. So this is one cycle. And then the other one goes from minus 40 down to minus 60, down to minus 40, down to this minus 20, down to minus 40. So this is a full cycle, this is a full cycle. What you notice here is that in this cycle here, it has a mean value, and this cycle here has also another mean value. But the two of them are called a block. So this is a block. And similar to what you will have in the crankshaft example. So we have kind of two blocks in this case. And what we want to do is calculate the damage as a result of the first block and the damage as a result of the second block, and add them together. But in order for us to do that, we cannot do them independently, so we will assume now that there is some kind of a connection between these, the dashed line, and this is going up again. So we replace this block with the one that has this dashed line. So the dashed line will give us a fatigue cycle that goes from 80 all the way down to minus 60 and back up to 80. And in addition, I have a small cycle here that goes from 40 from 40 to 60 and back up to 40. And then this cycle here from minus 60 to minus 20 and back up to minus 60. So in other words, this is kind of a simple way to break down the big cycle into 3 small cycles. One big cycle, which is going from here back up to here. So this is one cycle, and then the other is one here and one here. So we have 3 of them, and in this case we have the parameters specified for us are given here, that the ultimate strength is 151 KSI, the endurance limit is 67.5, and we want to estimate the number of repetitions of the stress time block, this whole block, that can be made before failure. So first step, in this case we don't have many stress components. We have only uniaxial type loading. We know the material data. We know F from the previous equation or the figure, and that will determine the 2 constants A and B that we have decided before, and therefore we have now a relationship between SF and the number of cycles that are allowable before failure. So next step is we're going to use Gerber fatigue criterion so that we can convert sigma alternating to an SF in case the sigma mean is greater than 0. If the sigma mean is less than or equal to 0, we can use it directly as SE, but this is not our case, so we have to use this particular one for the cycles at hand. So doing so, we can calculate now the for the big cycle the SF. However, there's just one simple step that we need to take, is that we wanted to make sure that there's actually the fatigue under any one of these cycles. We don't know if that amplitude is going to lead to a finite life or an infinite life. So this is kind of the, you notice that we have a very big cycle. We guess it should lead to a finite life. And then we have 2 little blips. We guess that they should lead to an infinite life. So in order for us to do this test, if you remember, we have to find the intersection between the load line, which is the ratio of the alternating to the mean stress level, and the bounding surface that we built based on either Goodman or Gerber or any other criteria. And we might even need to test the Langer line test to figure out if we would have yield on the first cycle. Suppose that this is not the case, then the only thing left is just to find the intersection between the load line and the bounding line based on, say, Gerber, for example. And we have the tables to go back and find the coordinates for this intersection. If the alternating stress is within, this is inside the surface or below the intersection, then we would have an infinite life. If it is outside the intersection, then we would judge that we have a finite life, and therefore we have to use the damage idea in the SN curve. So that's kind of the step that we should take here. So this is the load line. Sigma alternating of sigma mean is 7, and this is the coordinate of SA. That's the intersection between the load line and the Gerber line from the table, page 307. And therefore, when we find that this actual alternating stress is greater than the intersection point, therefore, the actual load point is outside the allowable zone, and therefore for infinite life, and therefore we should design for finite life. And to design for finite life, again, we calculate now the sigma reverse becomes SF, which is sigma alternating divided by 1 minus that fraction, which is sigma alternating over sigma mean square. Sigma mean over the yield strength of the material square, and that gives us 70.3. In other words, the influence of the mean is very small. It changed the fully reversed or the alternating component, and it made it a little bit amplified to 70.3. However, if the mean was very high, you would expect that this number to be very large, much larger than sigma alternating. Calculating the allowable number of cycles is 619,000, and therefore we can calculate a damage amount. So let's wait for that. So we have to go now to cycle number 2, find the intersection point is 24.2. Therefore, the intersection point is less than sigma A, and therefore we have infinite life. So we don't have to worry about it. Doing the same thing for cycle number 3, we get infinite life. And now we add up the damage fractions. Damage fractions, according to the simple Palmgren-Miner, is the sum of the number of cycles divided by the total allowable. And here we assume that we want to find the number of cycles, basically. So we just say we have number of blocks, and each block n has this fraction of damage, this fraction of damage, this fraction of damage. So when you add up the 3 fractions in a block, you multiply by the number of blocks, you will get this equation, and you solve for the number of blocks, you get 619,000 block cycles in this case. So this is basically the idea here. And now let's see what kind of modifications we will have to do if we want, in fact, to correct for a certain amount of damage that occurs to the material, so we can change the SN relationship if we go from one block to another. So that's the next step. So if we go here, we illustrate Miner's rule. So Miner's rule, let's say that the SN curve starts from 0.9 S ultimate at 1,000 cycles, and it goes to SE prime 0, which is the initial value of SE. So this is initial before pristine value. So everything is pristine. Now we applied 3,000 cycles, and we are allowed 8.52 times 10 to the 3. So we have left 5.52 times 10 to the 3. So this is what's left in the material. If we were to run at that level of the stress, we can run only up to 5.52 times 10 to the 3, which is essentially this point in here. So this point shifts. In essence, if I want to reuse the material, I must shift SF0 to SF1. Therefore, I can now do reconstruct the SN curve by finding the allowable number of cycles and assuming that I reach 10 to the 6 cycles here. So I have the coordinates of another point. This is 10 to the 6 cycles, and therefore I can shift the entire curve with that magnitude passing through this coordinates 10 to the 6 cycles at SE1 prime and SF1 that is determined from our damage calculations. Therefore, we have, this is the pristine now is no longer used, and then we can use the dashed line, or now I'm going to make it a red line, and that red line should be used for the second block that reduces the strength of the material. So you can see here that the strength of the material has been reduced, and I have effectively another material that is weaker. So the SN curve or SN relationship is lower than the pristine material. So in the case of the Miner rule, it's a little bit complex because we have to do some shifting. Therefore, Manson introduced an easier way to do it. An easier way, it preserves the fact that for 1,000 cycles, we know that failure is not going to occur below 0.9 S ultimate. So why don't we fix that point and then just use it as follows? So the Manson rule is a modification, and the Manson method is that the pristine curve, which is this one here, so the pristine curve is here for the first type of cycle in the block. Then the corrected or damaged curve in this case is pinned to the coordinates of 0.9 S ultimate, and therefore we recompute the point SF1 after the first utilization and just connect these two. So if we connect these two until we get to 10 to the 6, then we got a new level of the endurance limit, and this new level of the endurance limit is 34.4 rather than the original one, which was 40 before. So if you can see here, for pristine is 40, but here the reduction has been to 34.4. And then you can use this after first block. So these kinds of calculations make the design more exact and more complex at the same time. So we have to use them, for example, in our project if we want to do very detailed calculations, so we can account for the accumulation of fatigue damage from one cycle to another. Now, the last point that I wanted to add here before we close the lecture is what happens if I have a complex time structure of the stress versus time. In the example that I gave, it was just two blips, and then we connected them and we figured out that there's a large cycle and then there's two small cycles, and we added the damage. So what happens if I have a complicated structure? How accurate can I get? And this, I uploaded a document on the website that shows a method called the rain flow method that you can use in the design project, as we will see here. So in the rain flow method, which I will explain here, is very interesting, and the rain flow method shows that, so let me just kind of expand it here. So the rain flow method, suppose that I have a complex cycle, as you can see here, and I want to break it into half cycles, because sometimes half a cycle can make a big difference if you have low cycle fatigue. So I imagine that there's rain coming down on here, and these are rooftops, and the rain is raining on rooftops and running down. So you can see the rain is running down like that. Now the rules is the following. We start from one valley, so we have a one valley, and then we run the rain until we get to a valley, another valley, that is deeper than the first one. So started from 1, and then opposite to the valley, which is 9. So 9 is deeper than 1. 9 is deeper than 1. Therefore, we stop. And in this case, I have now half a cycle. So you can see all of this here is half a cycle. From here to here is half a cycle. So we're done with rule number 1. You start from a valley and you stop opposite another valley that is deeper. Rule number 2. You can also start from a peak like this one, and then you run the rain and you run it on top of all of the roofs until you stop at another peak that is deeper than the first one or higher than the first one. Of course, here we didn't have any higher, then we stop at the end. But in case you start from this peak here, then you rain down, and then you're going to stop at this peak, which is higher than 18 is higher than 14. So whether you are starting from a valley or a peak, you always stop opposite to another one that is either deeper or higher. Rule number 3 is that rain doesn't intersect. So if you rain down, you don't intersect with the one below. So you stop it. So if you have rain coming down, it doesn't intersect with the one that is flowing underneath. So that's rule number 3. So with these 3 simple rules, you can see that I can have half a cycle here. This is one half a cycle, another half a cycle small one, another half a cycle 5, and another from 5 I have to stop here because I can't intersect falling rain. 7 I have to stop because I can't intersect falling rain, and so forth. So this method is to be implemented, and I think there's a computer program that is uploaded on your website that can calculate this automatically, but for you, you can actually calculate it by hand. The upshot is that suppose that you have strain versus, this is strain versus time, you can convert it to stress versus strain, as you can see here. It's a cycle clothing. For example, you start from the top, and then this will be this part, and then you go down, so you're going backwards, and then you go up again, so you have another cycle here, and then you continue up to this point, you continue up to this point, you go down, so you're going down, and so on. So you can essentially project the strain versus time to stress versus strain, and this will be the cyclic stress strain diagram, fatigue diagram that we have to design for. So these are kind of the more accurate rules that we have, and I have an example here of a rod used in missile application, and it's under load, and the load varies, as you can see, from A to B, C, and so on. It goes in blocks. So the first load block is here, and this repeats itself every firing of this howitzer gun. You go through these blocks, and your job is to be able to convert all of these ups and downs to within one block. So you have to make it cycle 1, and then cycle 2, and so on, cycle 3. And each cycle you have to find sigma alternating 1, sigma mean 1, and so on. And then you have to find sigma reversible from these, and then calculate the damage 1, and so on. And this basically completes the idea of fatigue design that we will use in all of applications. There are many other aspects of fatigue, but up to this point we have accomplished quite a bit in fatigue design, and therefore we're not going to continue to look at surface fatigue and reliability associated with fatigue and fatigue of brittle materials. We will leave that for you to read on your own in the future, not for this course, but in the future if you continue to be a designer. But I think here you have acquired all of the knowledge that is necessary to be a good designer as far as fatigue design is concerned.